Hello, and welcome. Hopefully you enjoyed your little Accumulatown waiting room music. Welcome to this week's recitation. Today, as you can probably see, it is just me alone. Unfortunately, neither Lanton or Tyler are able to help me out today, so I'm just going to be working on my own, which on the bright side means that I can just stay in my room and do this without having to potentially go out or have to worry about interacting with people, and you don't have to have a listen to like me through a mask. That's Accumulatown from Black and White. I see from Pokemon Black and White. I saw someone ask about that. I'll try to shake up the music every week, get something different. But I'm a fan of video game music in general. Regardless, otherwise, going to be a pretty standard recitation today. Just from my room instead of from the COC. With that said, let's go over to my little scene that I'm going to be working with. So, just as some fair warning, I do understand that my handwriting is honestly pretty bad, so I've written out a lot of things in advance, so hopefully most of the things here are pretty legible. I do understand that just because I don't have to write things live doesn't mean that you don't have to write things live, so I will do my best to give you guys plenty of chance to write down all the stuff. I know people are going to ask, I'm not planning on uploading these notes that I have, but I will definitely make sure you have an opportunity to see them on screen if you want to just take a screen capture and save that for later. Obviously, the recordings of these will be posted, so you can look at them there. So hopefully everything will be pretty legible. I'll also try to say everything out loud as I'm like going through stuff so that you can tell what everything says. So your normal announcement today, homework 3, that's your deck homework, the one you've got right now, that is due September 8th. It did get extended. That's the Tuesday after this Labor Day 3-day weekend. The reason we extended it is because homework 3 is very based on linked lists for one of the files, and we wanted to try to get your linked list homework back to you before homework 3 was due. So, we wanted to... Sorry, I lost my train of thought. So we're not going to be able to get that homework 2 feedback to you until probably this weekend, so we extended homework 3 until after that, so you can have that feedback, have like a day or two to change it, and then submit homework 3 if you have any changes. Speaking of homework feedback, you all should have got your homework 1 feedback released today. Hopefully there weren't any issues with that. I know some things got weird with like the extension assignments and having 2 things. Please only submit to the regular assignment unless you've been explicitly granted an extension. It can get very messy for us if you submit to both when you're not supposed to. But all of the comments for that you can see on Gradescope. There are inline code comments and like a general comment applied to the submission. That general comment should contain all the sources of points that you lost on the homework with descriptions of like where they're from. If you notice a difference between those and your score, for example, maybe like the point deductions in the comment only add up to -6, but you got like a 90 on your homework, it is most likely something missing from the comment and not an error in the grade. You should still ask the TA that graded it about that to make sure and check to see what the difference was. But I'm just saying to not really get your hopes up that you're going to get points back. It's more likely you're just going to get more feedback that you missed by accident. Regrades are also open. You have to talk to a TA in office hours to get your request kind of approved through them. Then you'll submit your request officially, and then we will process it. And if we approve it, your grade will change. But no matter what, if you submit the form that the TA will give you, you will always receive some email back once we're done. It can take us some time to process those regrades. So, past that, homework 4, that's your next big thing. That is going to get released this Friday, September 4th. It's a 2-week homework plus an extra weekend past that, so it's going to be due on the 21st of September, so you've got quite a while. That's for a couple of reasons. First, homework 4 is a little bit of a longer homework than what you've seen so far. It's binary search trees, which we'll start talking about in lecture tomorrow, I believe. The second reason is because you have a test coming up on the 16th, and we didn't want to have it due on like the same week as you've got a test, so it's due a bit after that. But you'll see that whenever you get all this stuff. Your recitation worksheet, I think, might already be on the Canvas, otherwise it will get uploaded after this recitation. Again, campus and online Canvas, not the recitation Canvas. Big distinction. What we're going to talk about today, The big things are stacks, queues, and Deques, which Deques is the topic of your homework 3 that you've got right now, and obviously stacks and queues are very intimately related with that. Then, if we have some time at the end, which we should, we'll do a brief review of some iterable iterator stuff, which we talked about in lecture for a bit. We'll just take another touch on recitation. It's not going to be like a super in-depth dive into those topics. It'll just be a, like, if you forgot about it in like 1331, we'll remind you. It's not like we're going to test you on like a lot of the differences or anything. It's just something that's kind of useful to know. With that said, let's go and get started with our first big thing today, which is going to be stacks. Get that out there. So stacks are the next ADT we're going to be talking about. So up until this point, we'd only really been dealing with the list ADT, although we talked about 2 different ways to implement the list ADT. Now we're going to be talking about something entirely new, which is the stack ADT. Now, as we've mentioned, ADTs kind of provide the methods that we're supposed to implement without really telling us how we implement them. And the 3 that a stack has is it has a push method, a pop method, and a peek method. Push is how we add things to the stack, so we might say that we push something onto the stack. Pop is how we remove from a stack, so we can say that we pop things off of the stack. It's kind of where the lingo comes in. And peek is just looking at the top of the stack, so we take a peek at the top of the stack. Sometimes this is also called like the top method, just look at what's on the top. And these methods, like these method names, are pretty standard. Java's stack does use the same method names for these 3. You'll see with a queue it's a little different, but with a stack it's at least pretty consistent. And stacks follow the kind of LIFO property, LIFO, that stands for last in, first out. And what that means is when we put elements into our stack and then we take elements out, the last element we just put in the stack is going to be the first one we take out of the stack. So if we look at this example over here, we put in A first, and then we pushed B on top of it. So then when we pop something off, we're going to pop off B, because B is at the top of our stack, and it was the last thing we pushed on. So we pushed A, pushed B, then we would pop B, then pop A. What that means for like implementation-wise is that all of our adding and removing operations that we perform on a stack, those need to happen on the same end of the stack. So let's see how we do this in implementation. There's kind of 2 main ways that we implement a stack. We can either use an array or we can use a singly linked list. If we use an array, we're going to do our add and remove operations from the back. Because if you remember, removing from the back of an array is O of 1 time, and adding to the back of an array is amortized O of 1 time. So those are both pretty fast operations. Remember that we have to choose the same side for the operations. So if we chose the front of the array, then we'd be dealing with 2 O of n operations. So instead we choose the back. For a singly linked list, we're specifically going to generally use a singly linked list that doesn't have a tail pointer. The reason we do that is because if we had a tail pointer and we tried to do our operations on the tail of the singly linked list, we would have an add to tail, which is O of 1 time, and then a remove from back, which is O of n time, because remember you need to iterate to that second to last node. So even if we have a tail, we can't do the operations efficiently. So we're going to instead do our add and remove operations from the head. You remember both of those are O of 1 time to do. And since all of our operations are going to be on the head, a tail pointer would just take up extra memory and not get used at all, because we can use push, pop, and peek all with the head of our singly linked list. Now I know a lot of people are going to ask about this with stacks, queues, and when we get to Deques, about like when we would use one versus the other. I promise I will cover that a little bit more later. So we are getting there and getting to the differences between these, but people will ask about that a lot. So the reason we choose these operations, as I mentioned earlier, is because we want all of them ideally to be O of 1. Now, I guess I could put a little asterisk here because if you remember what I said, array has add to back being an O of 1 amortized, but essentially for most purposes that means it's usually an O of 1 operation, but that resize is something that we're going to consider when we compare whether or not we want to use an array-backed stack versus a singly linked list-backed stack. But the point is, for all of these data structures we're going to talk about today, we want all of our operations to be as fast as possible. If we're going to have slow operations, it's generally not going to be worth using them. It's going to be worth using something else. So some analogies that we often see with stacks is we use something like a Pringles can, or even I think like the Lay's knockoff brand is literally called stacks. If you think about a Pringles can, you can only ever reach the top of the Pringles can. You can't like grab a random chip out of the middle of the can. You have to grab the top one off, and if you want to put a chip back in your Pringles can, the only place you can put it is on top of the can. You can't shove it randomly into the middle through the side. That doesn't work. You only have access to the top. Something like a pile of laundry. You throw things onto the top of your laundry pile, and then once you eventually decide to like put it all into a hamper, or put it all into the washing machine, you're going to take those things off of that pile from the top. So you take the top thing off, then the next, etc. A more computer science analogy for a stack that we'll see a lot later in the course is recursion. Every time you make a recursive call to the method, it takes kind of the current frame that you're working in and puts it on top of the recursive stack. And you're always working kind of at the top of this stack. But we'll see that a lot later, especially when we talk about binary search trees. We'll see examples of kind of how recursion works in action and how we can use it in our data structures. All right, I will give a couple more seconds for people to write things down, or if they want to like take a screenshot of this, and then we'll go ahead and move on to queues. I'm not really going to show a lot of examples with stacks, because you guys have seen what arrays look like when you add and remove from the back, and you guys have seen what singly linked lists look like when you add and remove from the head. None of these operations are any different than anything we've talked about up to this point. So it's not really going to be a great use of our time to show examples that you've already seen before, just with a different title on the piece of paper. With queues in Deques, though, there will be some stuff to show. So we'll still be doing some examples today. And you can always look at some examples on the visualization tool. All right, I think I've stalled for enough time. So let's go ahead and pull this off. And look at our second ADT of the day, which is queues. Make sure that shows up. Yep. So queues are another ADT, separate from stacks, but very kind of on the same page. You generally talk about the two together. We have three main methods for a queue, just like we had three for a stack. We have enqueue, dequeue, and peek. And you notice I've written these here. That's because Java's queue, like Java's interface for a queue, calls the enqueue and dequeue add and remove. But usually in this class, we'll call them enqueue and dequeue, and in some other implementations, you may see them called enqueue and dequeue. But both names are pretty interchangeable. As the names would probably imply, enqueue is how we add elements onto our queue, and dequeue is how we remove them from a queue, just like we had push and pop for a stack. Also, if you struggle to remember the spelling of queue, enqueue, and dequeue, don't worry, it's kind of a mess. You just kind of alternate a lot of U's and E's at the end of the word, and it works out. The pronunciation's at least pretty easy, though. And peek is going to work the exact same way as it did with stack. We view the front of the queue, but we're not removing anything. You'll notice with stacks, I generally talked about like the top of the stack as kind of being where we were, versus queue, you generally talk about like the front of the queue versus the back of the queue. It's just a little bit of difference in language. You'll notice also when I talked about a stack, we had like this vertical representation, versus with the queue, we generally use a more horizontal representation. There's not really a particular reason for that, but it just kind of looks nicer and it fits better in our heads with how the operations actually work. So it's just kind of how things are. So unlike stacks, which were a LIFO structure, last in, first out, queues are a FIFO structure. That's first in, first out. What that means is that if something goes into the queue, and then we add like 10,000 more elements into the queue, when we remove, we should get out that very first thing we added to the queue. So if we look at this, what happened here is we added A to the queue, then B got enqueued behind it, and then when we remove, this A is going to come out first. So we added AB, and then we would remove AB, unlike the stack where we added AB and then removed BA. It's the opposite. And what that means for implementation is our stack had both of our operations happen at the same end, versus the queue is going to have both of the operations happen at opposite ends, and that's going to have some huge implications on how we have to use our data structures in order to get efficient operations for a queue. So, how can we back a queue? Just like with a stack, we can use either an array or a singly linked list, but we have to be a little bit fancier about how we do things. I'll start with the singly linked list because it's a lot simpler. If we use a singly linked list with a tail, then we can add to the tail and remove from the head and get two O of 1 operations from this. Notice if we switch them and we add to the head and remove from the tail, adding to the head is an O of 1 operation. Adding to the head is an O of 1 operation, so that's fine. But removing from the tail is an O of n operation. So that's a little bit expensive, and we're going to avoid that just by switching which side we add to. So it's kind of the opposite of a stack, where stacks we added and removed at the head, versus here we add to the tail and remove from the head. Also, someone might mention this, we could also back stacks and queues using a doubly linked list instead, but we can get the exact same performance with a singly linked list and not use all the extra memory that a doubly linked list uses. So I'm not really going to mention it here. But if you used a doubly linked list, you could kind of pick whatever end you wanted to add and remove to, provided that stack used the same end and queue used the opposite ends. But it's very rare in practice because you can use a singly linked list for the same purpose. Now, how do we do an array with a queue? Because arrays have O of n removed from... If we think about like array list operations, array lists have O of n removed from front and O of n add to front. So it kind of seems like no matter which side we choose to add to, we're going to be kind of screwed here with an array. But if we do a little trick and use them circularly, sometimes we'll say like a circular array, that is going to allow us to change our remove from front time from O of n to O of 1. And that is going to let us implement a queue with an array without using a really inefficient operation. Now notice I'm making a distinction here between array and array list. With a stack, we're basically just using an array list. I called it an array because we don't really need all the extra functions, but it met all the same properties. With a queue, we're going to be using an array in ways that would be illegal to use an array list, and you'll see why later. But if you remember, we talked about those properties that an array list had of being zero indexed and contiguous. We're going to be breaking both of those properties with a circular array when we use it for a queue. Some analogies that you might see with a queue, just like we talked about with the stack, is like a printer queue. If you send multiple jobs to the same printer, or if multiple people try to like print on the same campus printer, they go in a queue, so the first ones that get sent to the printer are the first ones that get printed, etc. Another example of a queue is waiting in line to get surveillance tested for COVID. The first people that show up in line are the first people that get tested. The people that show up later have to wait in line for a bit until it's their turn, and then they can get tested. Also, please get tested. President Cabrera just sent out an email to everyone about some COVID-related stuff. After this recitation, I recommend you check that out. But hopefully, I've stalled for long enough for most people to write everything on this page down, or take pictures of it for them to see for later. I can check if there's any big questions that I need to respond to, but all the TAs that are helping me out here have been doing a wonderful job at answering these questions. So thank you all to all the TAs helping me out here. For you guys in the restream, an hour and a half from now, I believe that's going to be Reese and Smitha today. Hope you guys are doing good. Hopefully all you people watching then are doing good too. And for all you people watching this back later at 2 times speed, hopefully everything's still understandable. I've stalled for enough. Let's take a look at an example, because circular arrays definitely sound weird, and it sounds like we should take a look at how they work. So here, I've kind of written out a bunch of the boxes and operations I'm going to be doing today for this example. I just want to kind of describe how I wrote things here. Up here is going to be my starting array for every operation. Then to the right, I've written the operation I'm going to perform, and that's going to leave me with the resulting array that's shown below it. So I kind of drew the arrows out for those first couple steps, but that's just kind of how I'm going to be writing things. So you'll notice I have an extra variable here that we haven't seen before when we deal with our array list. I have this f written here on index 0 of this very first array. This is going to refer to our front variable. It's going to tell us where the front of the queue is at any given time. So with an array list, all we had was a backing array and a size, but array queues are going to have backing array, size, and a front variable. Front is going to start at 0, and we're going to move it around as we perform our queue operations. So, when we enqueue something into our queue, we're always enqueuing to the back of the queue, because we want to pull things out of the front and put things into the back. So adding to the back of the queue is going to be really similar to adding to the back of the array list. So with a size 0 queue that has the front right here, when we NQ something in, that's just going to go at this index 0 spot. Now we have to think about where the front of the queue should be after this operation. Well, when we're just adding things to the queue, that shouldn't really change where the front is. The front should only really be changing once we remove things. So the front is going to be right here at the first element to remove. Now let's try adding some more things in. Let's say I try to NQ 2340 and then 1332. So if I'm just adding new things in, that means 1315 is going to stay in the same spot. Then I NQ 2340, so that goes right here in the back of my queue. And we'll talk a bit about how to actually find the back mathematically later, but for now you can just kind of visualize where the back of the queue is by where all the elements are. Then we NQ 1332, so that goes in the back of my queue. And again, the front variable is still here, because 1315 is still at the front of the queue. It's the first thing I removed. Now what's going to happen when we dequeue? So when I dequeue, I should be taking out the thing in the front of my queue. That should be the thing getting removed. So 1315 should get removed when I dequeue. Then I dequeue again, and that should remove the new front of my queue. So we understand that after this first dequeue, I need to adjust my front pointer to be over here at the new front of my queue. Then when I do my second dequeue operation, again, I take the front of my queue, I remove that element, and then I push my front pointer forward by 1 to reflect the new front of my queue. So I can write this down again here. This is what I've got. And you'll notice this array is not 0 aligned. So this kind of breaks the properties that we had with array lists, where we kind of start in the middle of the queue, where this front is. So now that we've dequeued some elements, let's try NQing some more things. So again, if we're only NQing, this 1332 isn't going to change, and the front pointer is going to stay the same. But when I NQ 2050, that goes in the back of my queue. So where is the back of my queue? Well, that should be after all of the elements currently in there, which is going to be right here for this. And again, we'll talk about how to find that in a second. So when I NQ a new thing, again, that goes in the new back of my queue. So you see, if we did some more dequeues, that would push this front forward and we would keep removing these things. Now, what happens when we try to NQ a thing after this? We try to NQ 1331. So I'll start again just by writing down the things I already had. So when we NQ something, we would look at where the back of this queue is. So we think, okay, well, I look at all my elements, and the spot afterwards is kind of right here. This spot after 2200. But that spot doesn't exist. Obviously, this is an index out of bounds exception. So how we compensate for that is with a circular behavior. So we treat it so that the element after the very end of our list is the same as the element right at the beginning of our array. I know I said list there by accident. I meant to say array both times. So the element after 2200, where this 1331 is going to go, is right here. So now we have this weird situation where our array is no longer contiguous. So again, this is why we can't use an array list. We have to use just a regular array that we kind of do the behavior on ourselves, because we can have it be not 0 aligned and we can have it be not contiguous. So now what happens if I add 1301? We think about the elements in our queue. Again, I'll write down the old ones. We think about the elements that were added to our queue. This is the one at the front, then we've got one here, then this is the next wraparound element after that, so it makes sense that when we NQ our new element, it kind of goes in this blank spot, which you probably could have guessed just by process of elimination. We only have one element. Now what happens if we try to NQ something to a full queue? Well, in this case, we're obviously going to have to resize, but unlike with an array list, we can't just kind of blindly copy over all the elements into our new queue. Because if we did that, you'd see this wraparound that used to exist wouldn't exist at this index anymore, because instead of wrapping around, it just kind of goes on to the next spot. So whenever we resize a queue, we have to kind of unwrap, or whenever we resize a circular array, we have to unwrap the array to realign it back at index 0. So that means the front of our queue is going to get moved right here to index 0. Now, how do we populate the elements after this? Well, we just keep going one by one. The next element is 2050. After that, we have 2200. Then we've got 1331. Then 1301. And you'll see I did that wraparound again after this. So this is the order of elements in this queue. These represent the exact same order because of the location of this front pointer. And then when we add our new element on, it very clearly is just going to go at the back of our queue, which is right here. So we have this example that we've worked out about a little bit on how circular arrays work. I'll talk about how we figure out this back location mathematically in a second. Otherwise, I'll give you guys a second to ask questions and for the TAs to answer them. I see stuff got pushed a little off screen. I think I can fix that though. So TAs can answer those questions or let me know if there's anything I need to answer. I do see the question. Yes, you do have the ability to ask anonymously. That is anonymous even to us. Please don't abuse that or anything. Otherwise, we may have to do some changes that we don't really like. But regardless, I think this is enough time to hopefully write down most of the rest of this. And then I'm going to show... Oh, I see some questions probably relevant. Can I explain the concept of a guard that Dr. Moss was going over? So I mentioned him say it I heard him mention it in lecture. Me hearing him mention that in lecture was the first time I had ever heard of that. So unfortunately, I'm not really going to be able to do it justice in an explanation. I would recommend watching his recent lecture video from Monday and seeing him explain it then, because he will probably do a much better job than me. All right, now let's see, how do we actually know where to add these elements when we're doing enqueue operations? So we have this back. Sometimes you'll see us represent it as a variable, but this is kind of the spot we're adding. How we can find this is we take our front pointer. So this represents where the beginning of the queue is. Now we want to go all the way past all the elements inside of it. So we're going to add an offset, which will kind of incorporate all of the elements in our list. That's going to be our size variable. And then now we need to account for the wraparound somehow. So how we do that is we take this sum of front plus size, and then we're going to do the modulus operator. Remember, this is like doing division and then taking the remainder, and that's going to be by the capacity. And remember, we can get this capacity just by doing backing array.length. So let's look in this previous example. Let me make sure that's on screen where I want it. Yes, in this previous example, when we did this add, how did we calculate this back index? Well, here, front was 2. Size was 3, and capacity was 5. So we did this calculation of back equals 2 plus 3 modulo 5, which is just saying 5 modulo 5, which is 0. So that is how we got that back, which is the index we're supposed to add at, is at index 0. I see someone asking if I can show other pages again. You should be able to rewind this and pause it even while I'm live and then catch back up to where I am. So if you need to do that for a second, feel free. If you if you show up a little late, you can actually rewind and then play back to the present live spot at double speed. So that is something that you have as an option to you. So we calculated that our back spot was index 0, and index 0 is where we added our new element. Then here, similarly, when we added in 1301 to index 1 over here, it's the same thing. We had front equals front equal to 2, size equal to 4, so we had 2 plus 4 mod 5, which is 6 mod 5, which is 1. And that's how we calculated that index 1 is where we were supposed to add this element. So this general calculation of front plus size mod capacity is how we calculate our back spot. We don't need a separate variable in order to keep track of it. We can do it just with our front and size. Now similarly, another good question is how we move our front pointer. So you'll notice when I should get this again, when I removed some of these elements, I had to move the front pointer forward. So how do we do that? So kind of the common way that people try to do this is they try to just do kind of your basic front equals front plus 1. But there's an issue that this doesn't really account for the circular nature of our linked list. Of our array. The circular nature of our array. Because what happens when front gets to the very end of the array? It's going to be kind of messy. So, just like we did with our back calculation, every time we want to increment front like that, we're going to need to mod it by the capacity. And that will cause it to automatically wrap around if we dequeue the last index of our queue. Then it will wrap back around to the front and we'll get this nice circular feature going on. So we'll come back to this page later a bit when we talk about Deques. Otherwise, we'll put this on screen for a second longer if you want to take a picture of it. You can always pause and do that too. And then we're going to, I'll keep this back on now, and then we'll be moving on to Deques in a second. Alright, that's hopefully enough time for everyone to catch up with stuff. I see someone asking if I can show how front will wrap around with the calculation. Let's give an example. Let's say I have a queue that looks like this, and I try to do a dequeue. What's going to happen is I remove 1332, I increment front by 1, and it wraps around to the beginning of this, because we have front equals 2 plus 1 mod 3, 3 being the capacity of the array, 2 being the old front, and we would get an empty queue with front here at index 0, because this is 0. That's what that would look like. Alright, Deques. Now Deques are a pretty cool data structure. They are the focus of your next homework, so hopefully that you guys have started to look at them. You guys have started to look at your homework. You've seen that your homework for this week is actually 2 different files. You have the ArrayDeck homework and the LinkDeck homework. Make sure you complete both of those files. Make sure that you put your name information on both of those files. It's very common for people to forget the name on one of them. I think I did when I took this class. But Deque is an abbreviation of double-ended queue. You'll see why a bit later. Some people wonder why it was double-ended queue and not double-ended stack. That's just because I guess the person that invented them liked the name Deque more than they liked the name DAC. And you may be wondering, Jacob, are you just using this long explanation as a way to show off your playing card deck collection while also subtly reinforcing the pronunciation of Deque? And I've got no idea what you're talking about. But either way, Deques are pretty cool data structures, so let's go ahead and start talking about them. As I mentioned before, it stands for double-ended queue. So a queue kind of forces us to add at one end and then remove from the other end. But with a double-ended queue, we can take our... with a double-ended queue, we can add at either end and remove from either end. So there's kind of no restriction on what end we can remove from. So you'll see with a queue, we had that like linear thing with one arrow coming in and one arrow coming out. But with a Deque, we kind of have arrows coming in and out of both directions. So we can add the C to the back, we can add the A to the front, we can remove from either side, completely free of choice. Which is pretty useful in a lot of ways. So we have 4 main methods for a deck, unlike the 3 we had for a stack and queue. We've got add first, add last, remove last. You'll notice I haven't written descriptions for these because I really hope that the names are pretty self-intuitive. Add first and add last, add to the respective sides and remove respectively. Sometimes decks also will have like peek methods, so like peek first or peek last. Those are pretty common, but we mostly like to focus on the add and remove operations, especially from like an implementation perspective. These are obviously much more interesting than just return head, return tail, or return index at front, or return index at back, etc. So these are the things we're going to be focusing on. There is 2 main ways we can back our decks. We can either back it with a circular array, that's going to be really similar to the circular array I just showed you guys with the array queue, or we can use a doubly linked list with a tail variable. So, if we do it with a doubly linked list with a tail variable, you'll notice I've specified both of these things here. We have to have a doubly linked list, and we have to have a tail. If we only have a singly linked list, you'll remember no matter how much we tried, there was no way for us to get our singly linked list to have O of 1 removed from back. We had to use a doubly linked list to accomplish that. And if we don't have a tail variable, then we can't accomplish that remove from back. So these are both very important things. I see someone saying their replies to questions aren't posting. I see a couple questions that were recently asked where like they're not published. One second, let me see if this is something I can fix. Let me try publishing those questions. Okay, those 3 aren't showing up. So hopefully Teams didn't completely break. But I'll at least answer the 3 questions I see that I'm not sure got answers. How does this work with negative numbers? The modules vaguely mention that. I will talk about mod with negative numbers with Deques because they don't actually matter for queues, they only matter with Deques. People are saying it looks like TAs have lost mod privileges. I can look at the thing for that and see. Every TA that's in there still says they're still a presenter, so I don't know where that happened. Maybe try refreshing it or loading it in desktop and see if that works. And then someone else asked what happens if front and back catch up with each other. That's going to happen when the array is full, and you can kind of think of it like it's a halfway decent indication to resize. You generally just want to use your normal size equals backing array dot length, but you'll see it visually. Sorry about that. I really apologize for this issue going on with the questions right now. I don't really know where it's coming from. Hopefully it fixes itself. I just saw a lot of new questions appear. By a lot of new questions, I mean the same question 5 times. So maybe it's fixed now? I don't know. We're gonna see. I've never seen this happen before. What was I going to? Circular arrays and doubly linked list with tails. Those are our 2 options. The doubly linked list with tail is going to work almost identically to how your homework 2 works. That's why we're trying to get that feedback to you before homework 3 is due. So all those operations are going to work the same. Circular array, that's going to be our main point of contention. That's intended to be like the actually more like difficult part of your homework. That should take you the most time. All right, now we've got our example here. Let me make sure everything's showing up right. Yep. So here, just again for reference, I had to use a slightly different representation of my operations to get everything to fit on one page. Here I kind of have the operations numbered, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And above every new array is the operation we're going to be performing to get that array. So this is our starting array. We perform this operation to get this operation to get this, etc., etc. Okay, it looks like questions are at least showing up, so I will try to answer some of these if it looks like the TAs still can't. TAs, if you regain the abilities to answer questions, let me know in Slack so that I can stop doing this. So you calculate back using front plus size mod capacity. Back isn't really a variable we have, so you can't do, you can't add the back to in your back calculation. It's not a variable we have. Yeah, it looks like the TAs got demoted somehow and they can't even see questions, and I don't know if there's anything I can do about that. I see someone saying they can. So Harrison may be the savior of everyone. Okay, they're saying they have the student view. All right, I will try to answer these questions as I see them. You can also ask questions on Piazza, and Piazza will allow you to, the TAs can answer them on that. I would recommend using private. You can do private or public questions on Piazza. Just try to be specific about what you're asking. I see a TA saying it's there's a server failure that they're seeing, but I will try to answer the questions I can see. Someone asked if we use a for loop rather than a while loop when going through the linked list, does that count as an efficiency deduction? No, for loops and while loops are equivalent. You can always write one as the other and vice versa. So it's never going to be an inherent efficiency deduction because of the type of loop you use. Okay. Hopefully this stays relatively smooth. All right, let's start with our deck. So we have this empty array here, and we want to add first 1315. So remember, when we added something to the back of our queue, it kind of went after all the elements. But when we add something to the front of our queue, it needs to go before everything. I see someone saying, is circular array the same thing as a wraparound array? Probably. It's almost, in this class, we're almost always going to call it a circular array. Dr. Moss may have said wraparound array at some point. He said back was calculated as back plus 1 mod capacity. We don't store a back variable inherently, so that calculation doesn't inherently make sense. If we were storing a back variable, that would be how we incremented it. So, again, when we add the first, we need to add it before the first element. So if our front is here, we need to go before that. So again, in a circular array, before index 0 is going to wrap around all the way to the end and be right here. And because we're adding a first element, this is kind of our new front variable. So front needs to also move with it and go around to the end. And that calculation is going to be a little different than how the stuff we did for our circular queue was. And I will do my best to show the differences in a little bit, but I want to try to get through this example first. So even though we only had an empty array, our add operation didn't put the item at index 0. It put it at the end of the list, which is kind of non-intuitive, but it's how these operations work. So when we remove first, that's removing from the front of the list. So this means we remove the element at the front, which is going to be the 1315, and increment front forward by 1, which wraps around all the way to the end. So we make sense if we do an add first, then a remove first, we end back up in our initial array state. Now let's look at some add last operations. This is going to work basically the same as our queue operations worked when we were dealing with our array queue, where we've got our front still here at index 0, then we add something onto the end, and then add something after it. And we can again calculate the spot by doing front, which is 0, plus size, which was 1, mod our length. So 0 plus 1 mod 5 gives us index 1, which is where to add this 1332. Now let's do another remove first operation. So when we do a remove first, that's going to be getting rid of the element at the front and then moving the front forward by 1. So we end up with 1332 here as our front variable. right here at index 1, or sorry, where our front variable is. Front is an index, not a piece of data. Now let's do some more add last operations. So when we do add last, the stuff at the front doesn't change. We add 2050 to the end of this, then 2200. Now we're going to do an add first. So as I mentioned, for an add first, again, adding isn't going to move around the elements we already have. We need to add it before the frontmost element. So kind of the steps we have for that are we're going to decrement front. So front moved from here down by 1, which is going to put it here at index 0. Then we add the element where our new front variable is. So these are kind of the steps for add first. Decrement front, put the element where our new front is. Now what happens if we do this again? All these old elements stay in the same spot. So we decrement front. Remember, that's going to wrap around and end up at the end of the array because we have a circular array, so everything kind of wraps around here. And then we add the element here. It looks like Landon has started a Piazza thread for asking questions during recitation, so you can go ahead and use that. Someone said, how did it go from 1 to 2? So remember our steps for adding to front. We decrement front by 1 and add element where front is now. So when we decrement front, it goes from 0 all the way to the end of the array because it's circular, which is here. And then we added our new element. So it's a little weird, but it makes sense in terms of our operations. You can imagine if we had an element here, in order to do an add first, it would need to go before that element. How do you decrement front? I will show that later. That's important. Why does front go to the end of the list? It is because our list is circular. We kind of went to index -1 because we went down by 1 from 0 and wrapped all the way around. So that is kind of the reason why. So let's do a resize. Just like before, when we do a resize in a deck, we need to make sure that we kind of unwrap the circular structure before we add our new elements in. Now I'm going to just unravel everything starting at index 0 and going forward. We always want to unwrap so that front is going to end up at index 0. This means if we were doing an add first to resize, we would actually have to use an empty spot here, leave an empty spot here for the element that we were trying to add. Okay, it looks like TAs can see questions now. So they're going to help me handle that. If that's wrong, let me know, but I'm pretty sure you guys can see questions now. All right, yep, Landon, sounds like we can see questions. Cool, so I'll let my TAs handle that, my other TAs handle that, and we will do this resize. So we start by copying over the front element, and then we're going to go one by one copying elements over. So the thing after 1301, we wrap around 1331, then 1332, then 2050, then 2200. And then now we add this 2110 to the end of our array. As a note, if this was an add first, we would have copied these elements over, shifted over by 1, and then added our new element in this spot here, just so that we don't already have this huge breakup as soon as we start. So we've done this. Let's take a look at some remove last operations. Remove last is, again, pretty straightforward. I don't think we haven't done any so far, but you can imagine what it looks like. The same as removing from the back of an array. So these elements at the front aren't going to change. And our front variable isn't going to change, but we remove these two elements at the end. Front variable stays in the exact same spot. Now, what if we do remove first a bunch? Well, every remove first operation is going to remove this element and push the front pointer forward by 1. Remember, add first pushes front backwards, remove first pushes front forward. So then we do it again. We do it a third time. We do it a fourth time. And we end up with our front variable here sitting in the middle of the list, and that is perfectly okay. We don't need to reset front to 0, we don't need to do anything fancy, we're just allowed to leave front in the middle of the list like this. That's perfectly acceptable. And I'm going to leave this on screen for a second. Oh, sorry, I need to shift this up. I think my camera got bumped around earlier, so the stuff that previously used to show on my screen doesn't anymore. But I apologize for that. So we just have this empty array with front here sitting in the middle spot. So, again, I'll leave this on screen for a little bit longer. You can pretty much see the stuff at the top too. So if people want to take a picture of that or just finish writing stuff down, then I'll go back, we'll talk about how to move the front variable around, and then we'll do a brief review of Iterator Iterable and try to end it off with a little bit of extra time just to help Reese and Smitha. All right. Let's take a look. Let's pull this page back up, because this is going to be a bit relevant. How do we decrement front? The really simple way that people are going to think to try to do it, and I'm going to write this out first, this is going to be a wrong way, and I'll explain why, is just to do kind of the exact opposite of we had up here. Front minus 1 mod capacity. And the reasoning and logic behind this is exactly fine. There's nothing wrong with the logic behind this operation. The only thing wrong with this operation is Java. Let me show you why. I'm going to make a little chart here. This is actual math. And this side's going to be Java. Let's do a relatively simple operation of -1 mod 5. In actual math, the answer to this question is relatively simple. It is 4. In Java, it interprets this as -1 mod 5. That's not like an order of operations thing, that's just how this operation is calculated, which it will determine is -1. And this is obviously not the answer we want if we're trying to always maintain a positive value in between 0 and 4 inclusive. So the reason this doesn't work is entirely a quirk of Java. It works in real math. Fortunately, we have written a nice little helper method for you that we call mod. And if we do mod of -1 and this is a function we wrote, it's not like it's a function that exists in Java, that is going to be correctly equal to 4. So on your homework, please make sure that you do the correct way, which is front equals the mod function we wrote of front -1 modded by capacity. Make sure you use this function whenever you are doing any subtraction or negative numbers involved in your wraparound calculations. You want to use this special function we wrote, otherwise you risk a lot of wrong stuff happening. So again, the logic behind this one isn't wrong, but it just doesn't mathematically do what you want. Finding the back is going to be the exact same as we did up here. Incrementing the front is going to be the exact same as we did up here. And remember, when you do your add to back and remove from back operations, those don't change the front variable at all, and we don't have a dedicated back variable because we can always find it with this equation. Okay. Things seem to be working all right. So, Deques are super useful structures. Obviously, from like an analogy perspective, you can use like a deck of cards as an example, because if you think about someone that's working with a deck of cards, the only real cards I can touch is I can get the top card of the deck, so I can access this, I can look at it, I can put something back on the top, I can remove a card from the bottom of the deck, I can put it on the top, but the things I can't do is I can't randomly shove cards in the middle of the deck, and I can't randomly pull cards out of the middle of the deck. The only things I can deal with are the top and the bottom as the dealer. Obviously, you want your deck to be pretty straightforward, so like if you have some card, you add it to the top of the deck, and then you remove from the top of the deck, you shouldn't get something completely different. You should get what you actually added. Nothing weird like that. I see some of the TAs are happy that I'm pulling out a deck. I don't have an actual like super crazy example, but if you can't tell, I love working with cards. I've done some card magic in the past. It might show up in future recitations. But you just want to make sure you do your operations. So you can't like take some element and like add it into the middle or anything. That's not going to get you what you want. That's just going to not work out. So you just want those elements on the bottom or the top. Those are the only things that matter. I don't really have fancier examples to show. Someone said do a trick at the end of recitation, maybe. I didn't have anything particularly planned. Oh, someone said just... Oh, I didn't remember that one. Okay. So this is most of the things with decks. So I promised I would talk about... I feel like someone just tried to make a pun in the question Q&A, and I'm sorry, but I don't get it. I apologize if your humor is above my head. Okay, I promised I would talk about array deck versus linked deck. So, most common question we see all the time is, if I want to implement a linked deck, all I have to do is use a doubly linked list, bam, throw it in exactly the same as my homework 2, that's it. If I want to use an array deck, I have to do all this crazy wraparound stuff, all this math, just to get my array deck to work. Oh wow, I'm dumb. Pokédex. I'm sorry. That has nothing to do with content and everything to do with humor. I'm really sorry I missed that. Okay, back to actual topics. So why would we ever use an array deck versus a linked deck when it just seems so much more complicated? And the answer is because from a practical perspective, not Big O, only talking about practical stuff, computers are really good at dealing with contiguous blocks of memory and operations on those blocks. Turns out that when people were optimizing hardware stuff, they decided that that would be a good thing to make really fast. So when we're dealing with these blocks of memory and all these like movement on them, that happens lightning fast at a hardware level. Versus linked lists don't get to make those same optimizations because the data is stored kind of broken up all over the place. So even though that array decks look like they should be a lot more complicated, they have this amortized O of 1 whenever you try to do the add operations. Despite all of that, in practice, array decks are much faster than linked decks for basically most purposes. And even thinking about like the resize cases, for like, let's look at like the stack resizing. People will be like, okay, well, your stack operations aren't quite as good because you have to potentially resize, but what if you're dealing with a stack that you don't want to resize? What if you're dealing with a stack where when it fills up, instead of resizing, you would rather throw a stack overflow exception because they overflowed your stack? So we can potentially make our stacks or arrays in the correct size that we would need before we start. That way we don't have to worry about these resize operations and we can just deal with our... Oh, that was... I should not try to talk and show off at the same time. I apologize. We can avoid having to do these resize operations and can instead just get the fast properties of our array deck compared to our linked deck, which does use less memory. There's your Pharaoh Shuffle. Okay. So, in practice, we use array-based decks and queues for a lot of things, despite them seem more complicated, they actually tend to work quite a bit faster. I think that's all the stuff I really wanted to talk about with stack skews and Deques. So now I will do a brief touch on Iterable versus Iterator. So this isn't really going to be content you're like tested on. You don't have to write an iterator for your homework. You never have to explicitly use an iterator on your homework. But it's something that's useful to know because it kind of comes up in the background a lot, and it's a nice thing to not be completely surprised by. So first of all, what is the difference between iterable and iterator? So we'll see this later. The one with the able at the end, the iterable, that's in java.lang. We don't need to import this. So no import. This is yes import. And iterable is an interface that when we have that interface implemented by some class, that means you are allowed to iterate over that class. So like list is an iterable thing. We can iterate over the stuff on our list. You'll see that when we have trees, that's something you can iterate over. Arrays are something you can iterate over. So as long as it implements this interface, you're allowed to iterate over it. In terms of a code perspective, what it means is that it has to implement a method named iterator, lowercase I iterator, and all that method needs to do is it returns a subclass of this iterator. So this is a lowercase of this that returns a subclass of this. A little confusing, but once you've worked with it a little bit, it makes some more sense. Iterator is something from java.util, which means you have to import it if you ever want to use it in your code, explicitly use it in your code. It is an interface for the objects that do the actual iterating. So this gets implemented by a data structure. This usually gets implemented by something like a private inner class or like a subclass or something. This is what does the actual work. You've got three methods here. So touch on how mod works for a second. I feel like I definitely did that on the previous page. Like, I have it written down here and everything. This is the differences with mod. I can show that again at the end if we have some more time, though. So, three main methods for the iterator. The next method, this is a huge misnomer that people get confused by all the time. It returns the data at the current point in our iteration and then moves itself on to the next. So if we think about like iterating over the words in this sentence, our iterator kind of starts here and then calling next returns this word and then moves our pointer forward by one. So next would return method, then is, then iterator, which returns a subclass of iterator. And then after returning iterator, it moves on to this spot after everything. So next returns where you currently add, essentially. Has next is going to check if there's any more data to iterate over. The hard and fast rule for has next is if has next returns true, then calling next should return some element. If has next returns false, that means if I try to call next, I'm going to get an exception. I'm going to get like a no such element exception. So in that example I just did earlier, has next always returned true until my pen got out here, past any words. The final method that we have for an iterator is remove. Remove is an optional method, and by optional method I mean basically no one implements it. But if we did implement it, it would be the only safe way that we're allowed to modify the structure in the middle of iteration. So like, while you're iterating over a list, you should not try to add elements to the list, you should not try to remove elements to the list, except explicitly using this remove method of this iterator, gotten from this iterator, by a class implementing iterable. It's a little confusing. It almost never shows up, mostly because no one implements this method. But it's there, and someday in the future it might be relevant to you. Literally over the summer I was implementing something where I had to iterate over a type of tree and do removals on that tree, and it was broken because actually a lot of other reasons not related to this, but I had to be very careful about how I did my removes during my iteration so that it didn't break everything. We've got Now here, you'll often see us mention this explicit versus implicit. If an object is iterable, we can kind of use both of these methods. They do the exact same thing. Someone said, did the video cut out? It did not cut out for my preview stream, so I really think it's fine, and I'm still getting good bitrate. So that's probably just an issue from you. I'm sorry. These do the exact same thing. They are almost literally the same thing. Doing this implicit just does this in the background. So with an explicit use of our iterator, we get our iterator using this .iterator method. That's this method. So this means that object implements this iterable interface. We have to have an import up here, I guess. So import java.util.iterator. That import is necessary, but it's kind of a little much for this. Then we do this while it.hasNext. Some item equals it.next. This is just a generic structure from implementing over every single item in the list. If you see this basic structure show up on anything, all that means is it's iterating through the entire list. I think some practice exam uses this. Some practice exam has a structure like this, or some recitation worksheet. This gets through everything. Implicitly, this is what we refer to as a for each loop. So this would be for every t item in object. This iterates over every single spot, getting our item at each point and storing it in this temporary variable. The big differences between these two is the explicit one gives you a bit more control. Like if you wanted to iterate 2 spots at a time, you could just call it.next twice, versus that's a little bit harder to do over here. If you want to do removals during your iteration, then you need this iterator explicitly declared in order to do that. But in general, these are pretty interchangeable, and you won't find yourself having to use this explicit iteration very often, but it does exist. So I will leave that for a little bit longer, and then we will be mostly done with the stuff that we were going to talk about today. I don't think there were any big topics that I missed. Hopefully, if I missed some major stuff, people in the restream will catch it immediately. But either way, I guess like 80% of the TAs wanted me to do a card trick. So that's all the content I'm going to cover today. If that's enough for you, you can leave. Otherwise, I'm going to do a quick card trick, and then we're going to end this off. Does the for loop belong to iterable or iterator? For loop is kind of just an inherent structure in Java. The for each loop here uses an iterator in the background because you're iterating over an iterable object. So, pretty basic. Let me get my camera out so I can see what it looks like. Pretty basic for ace trick. This trick deals a lot with like forces in Magic, so people would think that they're getting a free choice over what they're doing. I'll get this off. People think that they're getting a free choice versus in actuality, the magician's controlling whatever goes on. So if I'm choosing 4 aces, say I would ask a spectator to pick a random ace. A lot of people tend to pick the ace of spades because it's obviously a very common ace that people pick. So I obviously, as the magician, need to be prepared for that. So if we look at the backs of the cards, we can actually see that one of these cards has a different colored back, which is exactly the ace of spades. So I'm completely prepared for that, even though it sounds like they have a free choice. But that doesn't mean everyone's going to pick the ace of spades. There's a lot of people that want to pick the ace of spades, but they don't do it because they don't want to seem too mainstream or too predictable. So they instead go for the ace of clubs because it's kind of the other black ace. Obviously, I'm prepared for that too as the magician. If we look at the backs of the cards, one card has a different colored back, which is exactly the ace of clubs, because of course I'm prepared for that. Now, if they choose a red ace instead, probably the most common red ace I see is the ace of diamonds. People just don't tend to like the ace of hearts that much. And obviously I have to be prepared for the ace of diamonds, so if we look at the backs of the cards, only one card has a different colored back, and it's the ace of diamonds, that exact ace we just picked in this theoretical example. And finally, if I'm prepared for the other 3 aces, of course I'm prepared for the ace of hearts. With the ace of hearts, again, we look at the backs of the cards. Every card has one colored back, except for the ace of hearts right here. Now, people think that the backs of the cards really matter for this. It's not that important. As you can see, I'm just dealing with a bunch of blue cards here. I don't know if that one showed up on screen. Just dealing with a bunch of blue cards here. I can show you that again. All the cards have the same color back. It's not that important for the sake of this trick. Sometimes I even forget whether the cards I'm dealing with have a red back, maybe they have a blue back sometimes. It's not really that important. The basic idea is that their choices don't really matter in the grand scheme of the trick. What does matter in the grand scheme of the trick is I have just this one red ace, this second red ace, then this one blue ace, and this second blue ace right here, and these 4 cards are the only cards involved in the trick. Unfortunately, you kind of need to take my word on that, but if I was doing this trick in non-COVID times in person, I would let you examine these cards as much as you want. Only 4 cards in the trick, 2 red, 2 blue. And hopefully you've enjoyed this little recitation. You guys might see some more card tricks afterward. If you want to look up how to do that, I thought I remembered the name of this trick, then I realized I was thinking of a different trick. So I apologize. I am more than happy to show people how that trick works, though. It is based on a very simple principle called the Elmsley count. That works in a lot of tricks, but it's pretty cool. I think I learned this from a Million Card Tricks video, but I don't remember the exact name of the trick. So you can maybe find it. I might post a link to it in the recitation canvas later if I remember. Hopefully you've enjoyed this. I'm going to end this off a little bit early, again, just to give the people in the restream some more leeway, although I will give it about 30 or so seconds just because me ending it off in the present ends it off after the delay happens, so I need to wait a bit before actually ending the stream. But thank you for coming.